When we study small bodies from afar, the solar system looks almost abstract, points of light that move against the background of stars, faint spectra plotted as lines on a graph, resolution-limited images of irregular shapes. Telescopes and flyby missions tell us where these objects are, how they orbit, and give us a first glimpse of their surfaces. But they can never quite cross the final boundary, actually touching the material. The moment you bring even a few grams of dust from an asteroid or a comet into a clean laboratory on Earth, the story changes completely. Suddenly, that distant object is no longer just a pixel in a detector. It is powder on a metal tray, a shard inside a thin section, a grain under an electron microscope. The science stops being purely remote sensing and becomes laboratory physics, chemistry, and even geology. Sample return is, in many ways, a cheat code in planetary science. Instruments on spacecraft are always limited by mass, by power, by what was available at the moment the mission was designed. Once a probe is launched, its payload is frozen in time. A return sample works differently. A tiny grain of comet dust or asteroid regolith can be studied again and again, across decades, with instruments that have not yet been invented at the time of collection. We can measure its mineral structure with X-ray diffraction, map its isotopic ratios to parts per million, identify fragile organic molecules that would be impossible to detect from orbit, and even model how it formed and altered over billions of years. Each new generation of analytical techniques can extract more information from the same microscopic speck of ancient rock. Remote observations let us guess the composition of small bodies from their colors and spectra. Sample return lets us tie those guesses to reality. When we hold actual dust from a comet in a glove box on Earth, we can see which minerals form its rocky component, which ices were once present, and which organics survived the harsh radiation of space. We can ask subtle questions. How much deuterium is in this water? Are these organic molecules simple chains or complex ring structures? Did this material ever experience liquid water, or has it remained frozen since the protoplanetary disk? Each answer feeds back into our models of how the solar system formed, how volatiles were distributed, and how habitable worlds like Earth acquired their water and carbon. That is why the first dedicated sample return missions from small bodies were so transformative. NASA's Stardust mission flew through the coma of Comet Wild 2 and gently trapped dust grains streaming away from the nucleus, returning them to Earth in a re-entry capsule. For the first time, scientists could look at cometary material under high-resolution microscopes and see the surprising mixture of high-temperature minerals and primitive organics frozen together in a single grain, evidence of large-scale mixing in the young solar system. Shortly after, Japan's Hayabusa mission touched the tiny asteroid Itokawa and brought back a handful of microscopic particles. Those grains revealed a world that had been broken and reassembled, a rubble pile shaped by impacts, thermal cycling, and space weathering. They showed that even the smallest asteroids carry records of complex geological histories. A new generation of missions has pushed this idea further. Hayabusa 2 traveled to the carbon-rich asteroid Ryugu, fired a small impactor into its surface, and collected samples from both the untouched regolith and the freshly exposed subsurface. OSIRIS-RX visited the near-Earth asteroid Bennu, discovered a loose, fragile rubble pile with hydrated minerals and organic-bearing material, and then dipped down with a touch-and-go maneuver to scoop up a substantial sample for return. These missions do more than simply deliver rocks. They link what we see from orbit, spectra, albedo, morphology, to the true physical and chemical nature of the material. That connection lets us interpret countless other asteroids and comets that we will never visit directly, using the few we have touched as ground truth. In this episode, we will follow that shift from just looking to actually bringing pieces home. We will start with the logic behind sample return, and why it unlocks levels of detail that no instrument in deep space can match. Then we will walk through the first cometary dust from Stardust, the pioneering asteroid samples from Hayabusa and Hayabusa 2, and the rich, carbon-bearing regolith now returned from Bennu by OSIRIS-RX. Together, these missions have turned small bodies from distant curiosities into physical samples we can weigh, cut, heat, dissolve, and interrogate, tiny, tangible archives of the solar system's earliest moments, now resting inside laboratories on our own planet. NASA's Stardust mission was the first time humanity reached into a comet's breath and brought its dust back home. Launched in 1999, Stardust was sent to Comet 81P Wild 2, a relatively small icy body orbiting the Sun beyond Mars. Instead of trying to land, the spacecraft's job was far more delicate: to fly through the outer coma, the thin, expanding cloud of gas and dust around the nucleus, and gently collect microscopic particles racing past at several kilometers per second. The target was chosen because Wild 2 had only recently been perturbed into the inner solar system from a more distant orbit, meaning much of its surface material was still relatively fresh and less processed by repeated heating cycles near the Sun. To understand why this was such a bold step, it helps to picture the environment around a comet. As a comet approaches the Sun, its ices begin to sublimate, releasing jets of gas that lift dust grains into space. Those grains race away at high speed, forming the hazy coma and, eventually, the dust tail. Flying a spacecraft through this region is a little like driving through a sandblasting booth. Each tiny grain carries enormous kinetic energy, and if it hits a solid collector, it can fragment, vaporize, or damage the spacecraft. Stardust had to be engineered not just to survive this environment, but to catch these grains intact enough for laboratory study back on Earth. The key technological innovation was the aerogel collector. Aerogel is an ultra-low-density silica material, often described as frozen smoke, that is mostly empty space. When a dust grain traveling at several kilometers per second enters the aerogel, it plows a narrow track, gradually losing speed as the material cushions and decelerates it. Instead of shattering on impact, many grains remain largely intact, ending their journey embedded in a tiny carrot-shaped tunnel. Stardust carried a tennis racket-sized tray of aerogel tiles, which it exposed during its fly-through of Wild 2's coma in January 2004 and then safely stowed afterward for the trip home. Bringing those samples back was a complex choreography in itself. In January 2006, the sample return capsule separated from the main spacecraft and plunged into Earth's atmosphere at one of the highest re-entry speeds ever attempted for a human-made object. A carefully timed sequence of heat shield protection and parachute deployment delivered the capsule to the Utah Test and Training Range, where recovery teams retrieved it and transported it to a dedicated clean facility. Inside, embedded in the aerogel, were thousands of microscopic particles, the first solid material ever returned from a known comet. In the laboratory, researchers began the painstaking work of extracting individual grains from the aerogel using microneedles and then analyzing them with electron microscopes, mass spectrometers, and synchrotron X-ray beams. One of the most striking discoveries was the mixture of materials that formed under very different conditions. Some grains contained high-temperature minerals, including olivine and calcium-aluminum-rich inclusions similar to those seen in primitive meteorites, which must have formed extremely close to the young Sun, where temperatures were high enough to condense such refractory materials. In the same particles, scientists also found signatures of low-temperature ices and complex organic compounds, which could only have formed in the cold outer regions of the protoplanetary disk. This unlikely combination of fire and ice in micron-sized grains told a powerful story about the early solar system. It implied that material in the young disk did not stay neatly in place, but was vigorously mixed on large scales. Hot, inner disk material was somehow transported outward into the colder, comet-forming regions, while volatile-rich, icy material migrated inward. Comets like Wild 2, rather than being simple, untouched relics, turned out to be archives of this dynamic circulation, preserving, within a few dust particles, evidence of processes occurring across vast ranges of temperature and distance. Stardust also confirmed that comets are genuinely rich in organic chemistry. Analyses revealed a variety of carbon-bearing molecules, including complex organics that hint at prebiotic potential. While stardust alone could not answer whether comets delivered a significant fraction of Earth's organics, it strongly reinforced the idea that icy bodies carry more than just water. They transport a chemically active mixture capable of seeding young planets with ingredients relevant to life. Perhaps just as important as the scientific results was the proof of concept. Stardust demonstrated that we can collect material from a small, fragile body and return it to Earth without overwhelming contamination. The mission validated techniques for sample capture, sterile handling, and long-term curation, establishing protocols that later missions would build upon. It marked a turning point, from merely observing distant small bodies with telescopes or brief flybys, to physically holding pieces of them, slicing them, and interrogating them at the atomic scale with instruments that could never fit on a spacecraft. In that sense, Stardust changed the trajectory of small body science. It laid the groundwork for asteroid sample missions such as Hayabusa, Hayabusa 2, and OSIRIS-Rx, and it set the expectation that some of the deepest insights into planetary formation, mixing, and organic chemistry will come not from spectacular images alone, but from grains of dust, a few micrometers across, carefully preserved in boxes on Earth. The mission's legacy is still growing, as scientists continue to re-examine its samples with new techniques nearly 2 decades after they landed, exactly the long-term scientific leverage that sample return missions are designed to provide. Hayabusa, first asteroid sample, against all odds, 4 to 5 minutes. When Japan's space agency JAXA launched Hayabusa in 2003, the idea sounded deceptively simple. Fly to a small asteroid, briefly touch its surface, grab some dust, and bring it back to Earth. In reality, this would become one of the most dramatic and technically challenging sample return missions in history. Hayabusa's target, the near-Earth asteroid 25143 Itokawa, is a small S-type body only a few hundred meters across, a loosely bound rubble pile of rock and boulders drifting through space. For planetary scientists, Itokawa represented an opportunity to link a specific asteroid directly to the meteorites that fall on Earth, and to study how such small bodies form, evolve, and survive over billions of years. For engineers, it was a test of whether a relatively small spacecraft could navigate, rendezvous with, and land on an object whose gravity is so weak that a gentle push is enough to escape it forever. Hayabusa's mission profile required extraordinary precision. After a journey of more than 2 years, the spacecraft arrived at Itokawa in 2005 and began a detailed survey from close proximity, hovering tens of meters to a few kilometers above the surface using ion engines and delicate navigation. High-resolution images revealed that Itokawa is far from a solid rock. Instead, it resembles a distorted peanut made of boulders, gravel, and regolith, with regions that look like loose piles of rubble. This rubble pile structure is the result of a larger parent body that was catastrophically disrupted and then slowly reassembled under its own weak gravity. For a sample return mission, however, that kind of surface is treacherous, no flat plains, no guarantees of firm ground, and very little gravity to hold the spacecraft in place during contact. The sampling plan relied on a touch-and-go maneuver. Hayabusa was designed to descend autonomously toward a selected site, tap the surface with a small sampling horn, fire a projectile into the regolith, and let the ejected dust and small fragments drift up into a collection chamber. In principle, this avoided the need for landing legs or anchors. In practice, almost everything that could go wrong did. The spacecraft suffered reaction wheel failures, limiting its ability to control attitude. It experienced a fuel leak that complicated maneuvering. During one of the sampling attempts, communication glitches and sensor anomalies meant the team was not sure whether the projectile had fired or whether any material had actually been captured. At one point, Hayabusa had difficulty even leaving Itokawa's vicinity to begin the journey home. For months, there were serious doubts that the spacecraft would ever return to Earth, let alone bring back usable samples. Despite these setbacks, Hayabusa's operations team kept the mission alive through a series of careful workarounds and improvisations. The ion engines were operated in creative configurations to compensate for failures. Navigation was adjusted with razor-thin margins of error to preserve the remaining propellant. Eventually, in 2010, a small sample return capsule separated from the main spacecraft and plunged into Earth's atmosphere, landing in the Australian outback. When scientists opened the capsule in an ultra-clean facility, they initially saw only what looked like dust and tiny grains. But under the microscope, those grains turned out to be exactly what the mission had promised: genuine particles from the surface of asteroid Itokawa, measured in micrograms to milligrams, far less than originally planned, but scientifically priceless. Laboratory analyses of those microscopic samples transformed that tiny amount of material into a rich story about Itokawa's past. The mineral composition matched that of ordinary chondrite meteorites, confirming a long-suspected link between S-type asteroids and the most common meteorites found on Earth. The textures and chemistry of the grains showed evidence that Itokawa's parent body had once been large enough to undergo partial heating and metamorphism, before being shattered in a catastrophic impact. The fragments from that ancient collision later reaccumulated to form the rubble pile asteroid we see today. Surface grains also carried clear signatures of space weathering, subtle changes caused by micrometeorite impacts and the constant bombardment of solar wind particles, which darken and redden the surfaces of airless bodies over time. In other words, even a handful of dust motes held a record of thermal, collisional, and surface processes stretching back billions of years. Perhaps the most important legacy of Hayabusa is not just the data, but the proof of concept. The mission demonstrated that it is possible to navigate around a tiny, irregular asteroid, attempt touch-and-go sampling, survive multiple system failures, and still deliver pristine extraterrestrial material to Earth. It showed that even when everything does not go according to plan, careful engineering and persistence can rescue a mission and recover meaningful science. Hayabusa's success paved the way for more advanced sample return missions like Hayabusa 2 to Ryugu and NASA's OSIRIS-RX to Bennu, which were designed with improved hardware and benefited directly from the lessons learned at Itokawa. In that sense, Hayabusa was both a pioneer and a survivor, the first mission to literally bring back the breath of a small rocky world. When Hayabusa 2 left Earth in December 2014, it carried a very specific question into deep space. What does truly primitive, carbon-rich material from the dawn of the solar system look like, up close and in our laboratories? To answer that, JAXA sent the spacecraft to a dark, enigmatic near-Earth asteroid called 162173 Ryugu, a small world that reflects only a few % of the sunlight that hits it and that was suspected to be rich in water-bearing minerals and organic matter. Hayabusa 2 was designed as the successor to the trailblazing Hayabusa mission, but with stronger ion engines, more precise navigation, multiple small landers and, critically, the ability to deliberately blast a crater and sample freshly exposed subsurface material. After an Earth gravity assist and several years of quiet cruise, Hayabusa 2 arrived at Ryugu in mid-2018. From a distance, the asteroid immediately defied simple expectations. Instead of looking like a simple lumpy rock, it appeared as a dark, diamond-shaped body with a pronounced equatorial ridge, slowly spinning in the sunlight. Detailed tracking of its mass and volume showed that its bulk density is far too low for solid rock. The only plausible explanation is that Ryugu is a rubble pile, a loose collection of boulders, gravel, and dust barely held together by its own weak gravity, with significant void spaces hidden inside. High-resolution images confirmed this picture. The surface is a chaotic landscape of angular boulders and fractured blocks, with almost no wide, smooth plains. For a sampling mission, this was both scientifically exciting and operationally terrifying. Every descent would bring the spacecraft dangerously close to jagged obstacles in a gravity field so weak that a minor bounce or tilt could become fatal. Rubble pile structure tells a deeper story about Ryugu's past. Such asteroids are thought to be fragments of larger parent bodies that were once big enough to undergo internal heating and, in some cases, circulation of liquid water in their interiors. At some point, that parent body was catastrophically disrupted by a major impact. The fragments did not disperse completely. Instead, gravity slowly pulled some of them back together into a new, much smaller aggregate. Ryugu is one of those reassembled remnants, a compact cloud of debris from a water-altered, long-destroyed world. Studying its grains in detail is one of the best ways we have to reconstruct that ancient history. To touch such a fragile object without destroying it, Hayabusa 2 used a touch-and-go approach rather than a conventional landing. The spacecraft carried a sampling horn, a tubular funnel extending below the main bus, designed to briefly make contact with the surface, fire a small metal projectile into the regolith, and capture the resulting spray of particles as they ricocheted up into internal chambers. But first, the mission team had to find a place where the horn wouldn't collide with a boulder. Months of reconnaissance followed. From home position tens of kilometers above Ryugu, Hayabusa 2 mapped every ridge, depression, and block, building detailed digital terrain models and reflectance maps. Potential sampling sites were evaluated for slope, rock abundance, and navigation safety. Only after exhaustive analysis did the team select compact, relatively less hazardous zones, even if they were still scattered with stones. The first sampling operation targeted the uppermost surface material. During the descent, the spacecraft tracked its height with laser rangefinders and optical navigation cameras, comparing live images with stored templates to stay on course. In the final seconds, the sampling horn touched the regolith, the projectile fired at high speed, and a cloud of dust and small fragments was lofted into the horn. Almost instantly, Hayabusa 2 fired its thrusters and backed away, returning to a safe altitude while the precious grains settled into their canisters. The entire contact lasted only a second or two, but that moment converted years of engineering into a handful of true extraterrestrial soil. The second sample was even more ambitious. Hayabusa 2 carried a small carry-on impactor, essentially a high-velocity projectile deployed from the spacecraft itself. The mission released this device and then maneuvered behind the asteroid, using Ryugu as a shield. The impactor struck the surface at several kilometers per second, excavating a new crater and exposing subsurface material that had not been directly exposed to space weathering. the slow darkening and chemical modification of grains by micrometeorite impacts and solar radiation. After the debris cloud dispersed, Hayabusa 2 returned, imaged the fresh crater, and performed another touch-and-go maneuver to collect material from near this new, brighter patch. The result was a unique pair of samples, one representing surface-exposed regolith, the other sampling slightly deeper, fresher layers. In late 2020, a small re-entry capsule carrying these samples streaked through Earth's atmosphere and landed in the Australian desert. Inside were only grams of material, but those grams are among the most scientifically valuable substances on Earth. In carefully controlled clean rooms, scientists opened the canisters, documented every grain, and began a detailed battery of analyses. What they found confirms that Ryugu is one of the most primitive objects we have ever touched. Its composition closely resembles that of Ci chondrites, a rare class of meteorites that are chemically very similar to the Sun's overall non-volatile composition, and are considered among the least altered relics of the early solar system. Mineralogical studies revealed abundant hydrated minerals, especially phyllosilicates and other water-bearing phases. These can only form when liquid water interacts with rock, chemically altering it over time. This tells us that Ryugu's parent body was once large enough and warm enough for water to circulate through its interior, driving low-temperature aqueous alteration. Later, that parent body was disrupted, and fragments of altered rock, now containing water-bearing minerals, reaggregated to form the rubble pile we see today. In other words, Ryugu is built from pieces of a water-rich world that no longer exists. The organics in the samples are equally important. Analyses have identified a suite of complex carbon-bearing molecules, including amino acid-like compounds and other organic structures that can form through reactions between simple ices, minerals and radiation in cold environments. These molecules are not evidence of life, but they are clear evidence of prebiotic chemistry, the type of complex organic chemistry that could provide ingredients and pathways relevant to the emergence of life when delivered to a suitable planetary surface. Because the samples were returned in sealed containers and handled under strict contamination control, researchers can be confident that these organics are truly extraterrestrial in origin. Taken together, the hydrated minerals, isotopic signatures, and organics give a consistent picture. Ryugu is not just a random dark rock wandering near Earth. It is a chemically primitive, water-altered rubble pile that preserves material from a time when small bodies in the outer inner solar system were actively interacting with liquid water and carbon chemistry. That has direct implications for Earth's own story. During the early epochs of heavy bombardment, objects like Ryugu, water-rich, organic-rich rubble piles, could have delivered part of our planet's water inventory and a significant share of its prebiotic organic material. Instead of being mere hazards, such bodies may have been essential couriers of habitability. Scientifically, Hayabusa 2 proved several key points. It showed that sample return from small, low-gravity rubble piles is not only possible but can be done twice at the same object, including from an artificially created crater. It confirmed that C-type near-Earth asteroids can have compositions extremely similar to the most primitive meteorites, rich in hydrated minerals and complex organics. And it demonstrated that the fine-scale structure and chemistry of such bodies cannot be fully understood by remote sensing alone. Only by bringing grains into terrestrial laboratories can we measure isotopes, identify fragile organics, and reconstruct detailed histories of water-rock interaction and thermal evolution. In the broader context of planetary science, Hayabusa 2 marks a turning point. We are no longer limited to photographs, spectra, and flyby snapshots of small bodies. We can now hold their dust in our hands, weigh their grains, slice them, dissolve them, examine them atom by atom, and, decades from now, reanalyze them with instruments that do not yet exist. Ryugu's dark pebbles, collected by a small robotic emissary from Earth, have become a time bridge, connecting our laboratories today with the earliest chapters of the solar system's formation. When NASA approved OSIRIS-RX, the mission had a very simple but radical goal: do not just study a primitive asteroid from afar, go there, touch it, and bring part of it home. The target was 101955 Bennu, a small, carbon-rich near-Earth asteroid that, on paper, looked like a time capsule from the earliest days of the solar system. In practice, Bennu turned out to be even stranger, softer, and more scientifically valuable than anyone had predicted. The journey began with launch in 2016 and a gravity assist from Earth in 2017, setting OSIRIS-RX on course for a slow rendezvous with Bennu in late 2018. Because Bennu is only about half a kilometer across and has extremely weak gravity, The spacecraft had to approach it with exquisite precision. Over many months, OSIRIS-Rx orbited closer and closer, mapping the asteroid's shape, gravity field, surface textures, and spectral fingerprints of minerals and organics. Instead of a relatively smooth body with a few scattered boulders, as many models had anticipated, the cameras revealed a rugged world packed with rocks, ridges, and pits. It looked less like a solid mountain in space, and more like a loosely held cluster of debris, a classic rubble pile. Before a single grain was collected, remote sensing already showed that Bennu was rich in hydrated minerals. Spectrometers detected the telltale absorption features of water bound inside clay-like minerals and carbonates, evidence that Bennu's parent body once hosted liquid water circulating through its interior. The surface was also dark and low in albedo, consistent with carbonaceous material. For scientists, this combination, water-bearing minerals plus abundant carbon, was exactly what they were hoping to see in a candidate source of Earth's water and organic chemistry. Bennu was not just an interesting rock, it was a record of how volatiles and carbon-based molecules were distributed in the young solar system. The most dramatic moment of the mission came with the TAG, the Touch-and-Go Sampling Maneuver, in October 2020. OSIRIS-Rx descended slowly toward a carefully chosen site, extending its sampling arm and aiming a small circular head toward a patch of relatively open terrain. The plan was to make contact for just a few seconds, fire a burst of nitrogen gas into the regolith to stir up particles, and then retreat. What actually happened was a surprise even to the mission team. As soon as the sampling head touched the surface, Bennu behaved more like a fluidized, weightless gravel bed than solid ground. The arm sank deeply into the regolith, disturbing a plume of dust and pebbles that briefly surrounded the spacecraft. The resistance from the surface was far lower than expected, and the local material was so loosely bound that OSIRIS-Rx risked burying itself if it had stayed in contact any longer. Instead, the spacecraft executed its programmed back-away burn and pulled free, leaving behind a small artificial crater and a cloud of escaping debris. That single contact confirmed what the low overall density had been hinting at. Bennu has extremely low mechanical strength and is held together primarily by its own weak gravity rather than by solid rock. The good news was that the tag worked almost too well. The sampling head appeared to be overflowing with collected material, and some particles were even seen slowly drifting away because a mylar flap intended to keep them inside could not fully close. To avoid losing more sample, the team skipped a planned spin maneuver to measure the exact mass and instead quickly stowed the head inside the return capsule. When that capsule landed in Utah in 2023, recovery teams found that OSIRIS-Rx had returned around 120 grams of material, roughly twice the original mission requirement. For a primitive asteroid sample, that is an enormous scientific treasure. In laboratories on Earth, under ultra-clean conditions, scientists began to examine Bennu's dust and small pebbles grain by grain. The first major result was clear. Bennu is indeed rich in carbon-bearing material. The samples contain a wide variety of organic compounds, including complex carbon chains and molecules consistent with prebiotic chemistry. Unlike simple gases, these are solid organics locked into minerals and fine-grained matrices, the kind of material that could have been delivered repeatedly to the surfaces of young terrestrial planets. Equally important is the mineralogical evidence for water. Bennu's grains are full of hydrated silicates, clays, and other water-bearing minerals, as well as carbonates that form in the presence of liquid water. These minerals do not form in dry, airless space. They require a parent body where ice can melt, percolate, and chemically alter rock at relatively low temperatures. That tells us Bennu is a fragment of a larger, water-rich asteroid that once hosted significant aqueous alteration in its interior before being shattered and reassembled into the rubble pile we see today. The fine textures of the particles also carry information about the earliest stages of planet formation. Many grains are extremely small and primitive, preserving structures and compositions that trace back to the protoplanetary disk itself. Some components resemble known classes of carbonaceous chondrites, but Bennu's material also shows differences that highlight the diversity of early solar system reservoirs. Isotopic measurements, particularly of elements like hydrogen, oxygen, and nitrogen, allow scientists to compare Bennu's fingerprints with those of Earth's oceans, meteorites, and other small bodies. While the detailed analysis is ongoing, these measurements are already constraining models of how water and organics were mixed, transported, and finally delivered into the inner solar system. For the story of Earth, Bennu is a missing piece that connects several lines of evidence. Telescopic data had long suggested that carbonaceous asteroids could be rich in water and organics, But until OSIRIS-Rx, we had never held a well-characterized sample from such a body that we knew the exact context for its orbit, surface properties, and geologic environment. Meteorites that fall to Earth are fragments whose origins and histories are often uncertain. Bennu's sample is different. It comes from a known asteroid, from a documented site, collected in a way that preserves its structure and chemistry. That makes it a bridge between remote sensing, meteoritics, and numerical models of solar system evolution. In practical terms, OSIRIS-Rx shows that sample return from small bodies can be done at scale, even from fragile, loosely bound targets. In scientific terms, it confirms that water and complex organics were present in abundance on primitive asteroids and could have been delivered to Earth many times over during the age of heavy bombardment and beyond. And in a deeper sense, it reminds us that the ingredients for oceans and life were not confined to a single planet. They were mixed, scattered, and stored in countless small worlds, including one dark, spinning rubble pile named Bennu, whose dust now sits in terrestrial clean rooms and tells us what our solar system was capable of long before Earth became habitable. Across all these missions, a single picture begins to emerge. Small bodies are far more complex, ancient, and chemically rich than anyone expected when we first started pointing telescopes at faint moving dots of light. Stardust, Hayabusa 2, and OSIRIS-Rx all went to very different targets, used different sampling techniques, and returned different amounts of material, yet their samples tell a remarkably consistent story about the origins of our solar system. First, they show that many of these objects are not solid boulders, but delicately bound rubble piles. High-resolution images of Itokawa, Ryugu, and Bennu revealed worlds made of jumbled blocks, voids, and fragile regolith barely held together by their own weak gravity. Laboratory measurements of the returned grains confirm low bulk densities and mechanical properties that match a loosely consolidated interior rather than a single monolithic rock. That architecture records a violent past, larger parent bodies shattered in catastrophic impacts and then slowly reassembled, leaving behind asteroids that are more like floating gravel banks than solid mountains. The samples carry microscopic evidence of this cycle in the form of shock features, fractured minerals, and surfaces modified by space weathering. Second, the material itself is rich in water and organic chemistry. Dust from Comet 81P Wild 2 contains complex organics alongside minerals that formed at very high temperatures, proving that primitive ices and prebiotic molecules coexist with material forged close to the young sun. Grains from Ryugu and Bennu are loaded with hydrated minerals, clays, carbonates, and other phases that can form only in the presence of liquid water, as well as a wide variety of carbon-bearing compounds, including amino acid-like molecules. Even Itokawa, a more evolved S-type asteroid, shows the marks of thermal and collisional processing that link it to the ordinary chondrite meteorites that fall to Earth. Put together, these samples demonstrate that water and organics are not rare curiosities, but widespread ingredients in the small body populations that once crisscrossed the early solar system. Third, the combination of high-temperature and low-temperature components in the same tiny particles reveals that the young solar system was dynamically mixed. Material that formed in the hot inner disk was transported outward to comet-forming regions. Icy, volatile-rich material from the outer regions was scattered inward. The grains in the lab are physical proof that there was no strict, tidy separation between inner rocky and outer icy zones. Instead, radial transport, turbulence, and migration stirred the protoplanetary disk, blending ingredients across vast distances before they were locked into comets, asteroids, and eventually planets. All of this illustrates why sample return is irreplaceable. Remote sensing, spectra from telescopes, color filters on spacecraft, measurements of albedo and thermal emission, can suggest composition, but it cannot reach the same level of detail. A spectrometer can tell you that an asteroid's surface is consistent with hydrated silicates. A grain in a laboratory can tell you which specific minerals are present, how they are arranged, what temperature and pressure they formed at, and how they have been altered over time. Isotopic measurements are even more demanding. Ratios of different isotopes of oxygen, hydrogen, nitrogen, and other elements act as unique fingerprints for different reservoirs of material. Only by measuring those ratios with extreme precision in the lab can scientists tie a grain from Bennu to a particular class of meteorites, link that class to a specific region of the protoplanetary disk, and compare it with the composition of Earth's oceans and atmosphere. Samples also become a permanent scientific archive. The dust from Wild 2, the grains from Itokawa, the pebbles from Rygu, and the fine regolith from Bennu will be studied for decades. As new analytical techniques are invented, more sensitive mass spectrometers, higher resolution microscopes, new methods for mapping organic structures, scientists will be able to go back to the same tiny fragments and extract new layers of information. In that sense, each sample return mission is not just a single experiment, it is the creation of a long-lived library of early solar system material on Earth. Looking forward, this approach is set to expand far beyond asteroids and one comet. Mars sample return, building on the cores cached by NASA's Perseverance rover, aims to bring pieces of Martian rock and regolith back to Earth for the first time, opening a direct window into the planet's volcanic history, climate evolution, and past habitability. Concepts for future missions include returning material from metallic asteroids, which could reveal the structure of planetary cores, sampling other comet nuclei to explore the diversity of icy bodies, and, in the more distant future, collecting grains from icy moons or even Kuiper belt objects far beyond Neptune. Each new target would add another chapter to the story that small bodies are already beginning to tell. Taken together, the results from Stardust, Hayabusa, Hayabusa 2, and OSIRIS-Rx show that touching ancient rock is not just a technical milestone, it is a profound change in how we study our cosmic origins. Instead of guessing at the chemistry of the early solar system from afar, we now hold some of its ingredients in our hands. Every tiny grain from Bennu, Rygu, Itokawa, and Wild 2 is older than any rock on Earth. They are the pages of a book about how our solar system, and worlds like ours, first began. For this episode, the script and all scientific claims will be consistently checked against a small set of primary, mission-level and peer-reviewed sources, rather than popular summaries or secondary blogs. The backbone for everything related to Bennu and OSIRIS-Rx will be NASA's official mission documentation and science releases. These include the mission overview, trajectory, and operations reports, the tag sampling description, and the post-return laboratory results on carbon-rich material, hydrated minerals, and isotopic signatures. They provide the authoritative numbers you care about: sample mass, density, mineralogy, organic inventory, and key conclusions about Bennu's role as a potential carrier of water and prebiotic chemistry. For Hayabusa and Hayabusa 2, the reference layer will be JAXA's own mission reports, press releases, and published summaries of Itokawa and Rygu sample analyses. These materials fix the timeline, launch, rendezvous, sampling, and Earth return, confirm spacecraft issues and upgrades, and summarize what was actually found in the grains. Chondritic composition for Itokawa, CI-like, water-altered material, and complex organics for Rygu. Evidence of rubble pile structure and low-temperature aqueous alteration on the parent bodies. Whenever the script mentions specific properties, low bulk density, hydrated minerals, amino acid-like compounds, porosity, those details will be cross-checked directly against JAXA and mission team publications. The Stardust segment will lean on NASA's Stardust Mission Archive and the key sample analysis papers that followed the return of dust from Comet 81P Wild 2. These sources constrain the capture method, aerogel collection and return capsule, the mix of high-temperature and low-temperature components in the grains, and the evidence for large-scale radial mixing in the early solar system. They also underpin any statements about the diversity of organics and the coexistence of inner-disk minerals with outer-disk ices in Planetary material. To connect these mission-specific results to the broader picture of primitive material in the solar system, the script will also draw on review papers and data compilations in journals such as Science, Nature Astronomy, and Meteoritics and Planetary Science. These works summarize the state of knowledge on CI and other carbonaceous chondrites, isotopic fingerprints of different reservoirs, and the emerging synthesis from all sample return missions. They are essential for framing statements about the prevalence of water and organics, the dynamical mixing of the protoplanetary disk, and the links between comets, asteroids, meteorites, and the volatile inventory of the terrestrial planets. Taken together, this set of sources will be used to calibrate every quantitative claim, sizes, dates, densities, sample masses, every qualitative conclusion, rubble pile structure, degree of aqueous alteration, complexity of organics, and every broader statement about the role of small bodies in delivering water and prebiotic molecules. The goal is that every sentence in the final script can be traced back to mission teams' own releases or to peer-reviewed syntheses, so the storytelling stays cinematic while the facts stay anchored in the best available science.